Together with my colleague, we will be discussing our thesis paper entitled An Empirical Analysis of a Decentralized Approach Using Blockchain Technology for IoT Devices. So this will be the overview of our presentation, the introduction and related literature by me, and then my colleague will discuss methodology, the results and conclusion, and lastly, I will be discussing the recommendations. So for the background, the Internet of Things are big and it's getting bigger. So according to the International Data Corporation, they estimated 41.6 billion connected IoT devices by 2025. And as the IoT continues to expand, it is increasingly shaping the digital landscape by connecting the physical and digital worlds. However, in a study by HP, 70% of the most commonly used IoT devices contain vulnerabilities. So this is still one of the main drawbacks of IoT devices, which is security. So these vulnerabilities can be attributed to the constraints of IoT devices in terms of their computing power. This limits their use of high resource functions needed for security. So one way to address this is through authentication. Authentication can restrict access to protected resources, therefore enhancing IoT device security. So there are many ways to implement authentication, but the most popular way is through centralized database systems where the user credentials are stored. But the main problem of centralized database systems is single point of failure. This happens because data is stored in one location and a single server or a computer is responsible for processing a client request. This architecture presents many issues and challenges such as slow processing time, server failure, data collision, and also data leak. So in terms of authentication, a compromised centralized server would expose sensitive user data, posing a considerable risk to IoT device security. Our proposed solution is to use decentralization. Decentralization is the process of dispersing power away from a central authority, therefore reducing the issues of single point of failure. So our goal is to create a system that will grant users access to their IoT devices using the ESP8266 module. So this module is a low power and low cost Wi-Fi development board that facilitates the IoT communication through the MQTT protocol together with a Mosquito broker. So by implementing a decentralized authentication protocol such as the blockchain technology, we can leverage its transparency and immutability to create a robust authentication system. To store our data, we will be using the CockroachDB distributed database. So this database enables us to distribute the data across multiple locations, therefore reducing the risk of data loss, ensuring resilience in the face of failures. And then we will then compare the performance and security of our decentralized approach to a centralized implementation using the Passport.js JWT package authentication. So all in all, our research aims to provide an empirical analysis of using blockchain technology for IoT devices in order to offer valuable insights into the potential advantages of adopting a decentralized approach to IoT device authentication. So next, I will be discussing our review of related literature, starting with the blockchain. So blockchain technology has emerged as a powerful tool in the modern digital landscape. According to the study by Ili Humo, blockchain is a decentralized and distributed database technology. So this provides a platform for transaction and data management where users can be secure because they have control over their own data. So this is one of the most notable features of blockchain as described by Ray, because all of the data is only accessible by the user using their own cryptographic digital signature. And another functionality that is brought about by the blockchain is that it enables the use of smart contracts. Smart contracts are self-executing contracts between two parties where the terms of the agreements of the contract is found in the code itself. So according to Frankenfield, this creates a trusted agreement among parties without the need for a centralized authority. So this eliminates the centralized authority, therefore reducing the issues of single point of failure. And in a study by Mayer, in recent years, we have seen a surge in a trend of blockchain as a service and its integration into IoT. So basically, this demonstrates that there really is a potential of using the blockchain to disrupt various industries and redefine the way we interact with technology. So the Internet of Things is a network of interconnected devices that has become increasingly prominent in recent years. And while the low-cost computing aspect of IoT devices has contributed to their spread and prominence, it also exposes a critical weakness, which is the security processing gap. This was brought up by Nina in their study, and they described this gap as the inherent limitations in security processing capability of IoT devices, making them vulnerable to various attacks such as physical tampering, malicious software, and side-channel attacks. In a study by OWASP DAG, common vulnerabilities also include lack of proper authentication and encryption practices, and lack of access control to prevent unauthorized remote access. And in a study by Bertino, as the Internet of Things get more and more prominent, addressing these challenges will require a more long-term approach. And this is such as the implementation of a more robust authentication methods for IoT systems. So next we will explore authentication, which is a critical aspect of digital security. There are two major authentication methods, which is the personal access tokens and also session-based authentication. And under the personal access tokens is the JWT or JSON Web Tokens, which is a popular authentication technique that uses tokens for encryption, providing a secure way to authenticate users and to encrypt data that is transmitted over the network. In line with this, Passport.js is an authentication middleware for Node.js, which supports both session-based and token-based authentication and houses more than 500 comprehensive strategies. So this flexibility and modularity makes it an ideal choice for integration into various express-based web applications, such as the one that we have implemented. Lastly, to highlight some related works, we have the work by Mina and Yang in 2018, where they proposed a blockchain-based gateway that will be able to identify and to authenticate valid users as defined in a smart contract. So in their study, the actors that pass the authentication test will be placed in a whitelist, therefore enabling the communication between the network. Another study is DAuth, which was introduced by Shibashi. So in his study, they utilized smart contracts to authenticate users and to store data in centralized servers. This provides a more secure alternative to the traditional centralized authentication system. And lastly, we have the study by Kadali and Koratka entitled MQTT-based Home Automation System using the ESP8266. So this system is a home automation system that uses the lightweight protocol MQTT to enable communication that uses low bandwidth and less power. And this system was also deployed in an ESP8266 Wi-Fi development module.
So for the methodology, I'll be discussing three points. So the first part will be the conceptual framework. So this is the visualization of the process behind each system design. Next will be the research procedure, which will be the process of how the data has been stored. And lastly, will be the testing phase, which is the computations used in the verification, validation, and testing phase. So for the centralized authentication system, the process starts when the user registers or logs in to the website, which looks like this. So this is our sign in and sign up page. And once the user has successfully logged in, he will be redirected to this dashboard. So you can see here, you can choose the type or thing type, which is the device, in this case the sensor. And he or she can register the device and also change the state of each of the device. Next, these states are stored in a MongoDB server and together with the user credentials. So once the user performs any actions that will require the sensors, it is then sent as a request to the internet and then the request is then received by the Mosquito server or MQTT server, which and then after is approved and then sent to the router, which sends the request to the ESP module and then finally communicates directly to the sensor. So for the centralized authentication system, the user will have to register and log in to the website, which will look like this. So it's like a sign in and sign out page. And then he will need to use a MetaMask wallet, which will hold the address, which will act as the user credentials for this type of system. And then once the user registers or logs into the page, a smart contract will be deployed. So as you can see here, the rightmost image is when the user will register for the first time. So there will be a one-time transaction for the user credentials to be saved on the blockchain. And the left is when the user will log in or sign in to his account. All he needs to do is sign a signature, which will authenticate if he is really the user for that account. And then once he's been logged in, he'll be redirected to the dashboard. So it's similar to the centralized authentication system. And then to explain on how it communicates to the blockchain, we'll be using hard hat as the testing environment. So in this case, we'll be using Ethereum, and then for each transaction, it will go through a network of peer-to-peer systems, which will authenticate and authenticate the transaction without a middleman. Next, it will be sent to a block miner that will validate if the transaction is approved, and the block miner will attach the transaction on a block, which will then be connected to the blockchain and then connected to access to the internet. Once the user does any actions again, such as register a device or change the state of any of the device, it will be stored in the MQTT server, and for the states, it will be saved on the Cockroach DB, which is a distributed database. So similar to the centralized authentication system, it sends a request to the router, which sends the request to the ESP module, which communicates to the sensors. So this is the sensor setup. So as you can see here, we have the LED, temperature, sound, motion, and heart rate. And lastly, the ESP8266 module, which will help communicate with all the sensors. So the sensors here act as an alternative to real IoT devices, which will fall under these categories. So the research procedure. So first, both of the systems will be tested using Apache JMeter and the OS WhatsApp testing tool. So the Apache JMeter will be used to test the performance of both systems, and it will use a thread group with 5 iterations, with having 50 threads within each iteration. Next, the OS lab will produce a list of risks or possible risks and security alerts that will be shown later on. So for the testing, performance testing formulas will be using these. So ALT, or the average latency time, will be using the latency time over the total number of requests. The latency time is the time that it takes for the data to pass from one network to another. Next will be the error rate. So the variable that we'll be using here is the disconnect rate. So this is the time when the client will be disconnected from the network. So this is usually calculated in milliseconds. Then you multiply it by 100 to get the percentage. Lastly would be the average connection time, which will get the average connection time delay between the client and the server or database. So in this case, in Apache JMeter, if it does not have any delays, it will show 0. So these are the list of possible risks for each alert of this app. So in this case, you can see, I'll just discuss this later. This is a continuation of the possible alerts and risks. So the risk that I would want to explain briefly would be cross-site scripting attack. So this is when a user is sent a link and to click, which allows the attacker to run a script in the background without the user knowing. Next would be horse-based attack. So horse or cross-origin resource sharing is a browser mechanism which enables controlled access to resources located outside of the given domain. So if this is not properly configured, it can be accessed by any attacker and also manipulated by them. Next would be clickjacking attacks. So this is the most common. You can see this in ads or pop-up ads that are shown in various websites that make you click on them and then it redirects to another page doing something else. Okay, so for the results, this is the table of after 5 iterations. So for the decentralized authentication system, the total average was 218.75, while the centralized authentication only had 115.98, which is around 1/10 of a second different, since this is 10 milliseconds. So next would be the error rate. So the decentralized authentication system has a consistent 0.00%, while the SAS system had a 3.37%. Next would be the performance connection test. So the average connection time of the decentralized authentication system was 2.16, while the centralized authentication system has 4.85 milliseconds. So there's quite a difference there. Next would be the risk levels of the decentralized authentication system. So this shows that there's a significant difference in the informational part, which will be explained in the next slide. So these are the list of instances of alerts in both systems. As you can see here, the information disclosure or / suspicious comments and modern web application has of the decentralized authentication system is lesser than the centralized authentication system. So conclusion. So these are the key findings as what I've discussed before. I wanna emphasize that for the decentralized authentication system, there were lesser packets that were dropped during each request. And then for as our conclusion, we would say that centralized authentication system is a better alternative for the following reasons. So all packets were sent and received from both endpoints, as you can see as the error rate was 0%. There was a low risk level compared to the centralized authentication system. There's little to no server downtimes. Most of since the data were stored in distributed databases, which are not centralized, which is not centralized. And lastly, accounts are stored in the blockchain to avoid single point of failure.
So after developing our system, we have noticed that there's still lots of improvement that can be done. The first of them is the use of different IoT devices other than the ESP8266 module. So this is because the ESP8266 module is a module that has already been specialized for communication and processing. This would mean that the data gathered may be better when compared to other IoT devices. And then our next recommendation is the use of the blockchain itself to store the states instead of the approach DB. So this is because the blockchain is immutable and transparent as compared to the approach DB system. So however, one thing that needs to be addressed also when using the blockchain itself is also the speed and the cost of using the blockchain directly. And then the next recommendation is to deploy the system to a live blockchain. So currently our system is using a test network for the testing, and then if it is deployed in a live blockchain, the data may be different once deployed. But there's also a concern here into the cost of deploying the smart contract to a live blockchain, and also the cost of interacting with the smart contract. And lastly is to explore other authentication methods for the centralized authentication system, and also for the decentralized authentication system, in order to benchmark the performance of other authentication methods before drawing a conclusion. So that is all for our presentation.